All right, guys, welcome back. Here we are focusing on our last set. This will be part 3 of our exercise set for 1.1. And then we will be done with the first section of chapter 1. So we'll tie in our real-world problem here. I did want us to focus on the chemistry problem, as Algebra 2 oftentimes prepares us for chemistry, or helps us to practice concepts that we cover in our science classes. Then we'll be moving on to 1.2. I'll give a preview here. 1.2 we'll be working with properties of real numbers. And if we go way over here, we'll be working with the Pythagorean theorem as well, slightly, as we connect that to algebra. But let's go to our chemistry problem here. In chemistry, scientists use numbers to classify and compare elements. So, in other words, the same skills that we've been using for number sets will apply here. But here we have our elements from the periodic table. Here's our table. And we want to, number 22 says, order the given elements from least to greatest atomic mass. We can begin there. So we'll be looking specifically here at the atomic mass column, AMU, short there for atomic mass. And if they aren't in decimal forms in a column, you would be, converting to decimals, but here they already are because this is atomic mass. And we just want to order this from the smallest to the largest. So in other words, which element has the smallest atomic mass, and we'll go from there. So here we have lithium at 6.941 AMU. Atomic mass. Now we have aluminum will be next at 26.982. And then sulfur will take number 3 at 32.066, and then chlorine will take the number 4 spot at 35.4527, and finally number 5, calcium, at 40.078. All right, now that we have those in order, let's go ahead and write that out. We can write our answer in abbreviations here from the periodic table to save room here, but our answer will be first lithium, and then aluminum, then sulfur, then chlorine, and then lastly calcium. All right, that's least to greatest atomic mass. We can label that least to greatest atomic mass. Now let's take a look at number 23. Which subset of the real numbers best describes the atomic masses of these elements? Choose from R, Q, Z, W, and M, which we've been working with throughout the video series here for the first section here in chapter 1. So let's continue that skill. We can look at our atomic masses. Let me erase this part. And we have 26.982, 40.078, 35.4527, 6.941, 32.066. What kind of numbers are these? For example, are they integers, or do they have decimal parts? Can they be expressed as fractions of integers? Here we have decimal parts. They are terminating decimals, so they can be expressed as fractions. They are rational numbers. So let's go ahead and put Q. More specifically, they're positive rationals, so that makes them also real numbers for our R. And of course, they're all real numbers. All right, now we have real numbers, rational numbers, and that will do it. Q and R. Let's take a look at 24. Which subset of the real numbers best describes the ionic charges of these elements? Choose from R, Q, Z, W, and N. Let's take a look at our ionic charges. So we have positive 3, positive 2, negative 1, positive 1, negative 2 for our ionic charges. And the question is, are these whole numbers, integers, rationals, or irrationals for our abbreviations here? They are integers, both positive and negative whole numbers for integers. So we're going to put Z. They're also rational and real. ZQR. And number 25, explain why interval notation cannot be used to represent the set of atomic masses given. So let's recall what interval notation describes and ask ourselves, does it work for all sets? In other words, does interval notation describe individual separated values or a continuous range? And in this case, it's a continuous range. The atomic masses are 5 specific individual values, not a continuous range. So if we wrote 6.941, 40.078 with open and closed brackets, that would include every real number in between, like 10.2 or 25, which are not atomic masses of these elements. So let's keep that in mind. Put a line through that. Interval notation cannot be used because the atomic masses are 5 specific isolated values, not a continuous range. Interval notation would incorrectly include all the real numbers between them. So, that's the key conceptual point, is that interval notation describes a continuous set of real numbers, not individual points. So let's go ahead and complete our notation table as we move on. Or actually, never mind. We're not going to do that part. So we'll go ahead and call it an end here at 25. Now, so we can jump right into our next section, 1.2, not waste any time on that. Thank you for joining. This is the end of 1.1. So go back in our previous videos if you haven't had the chance to. Foundations for functions was our very first. Just a few warm-up exercises there to get us into the course. In this first section, we worked with sets of numbers. As you can see, all our videos covered all the way through to our chemistry problem here, which we just did today, 22 through 25. Take care, and we'll see you soon. Bye.